In module 1, we started with a brief introduction of Legendre's polynomial. We have also given the solutions of Legendre's equation, which is Legendre's polynomial of first kind and Legendre's function of second kind. In module 2, we will look into the generating function of Legendre's polynomial. We will also derive an alternate expression for Legendre's polynomial, and this will be followed by 6 examples which will clarify this module 2. We now look into the function that actually generates Legendre's polynomial. The origin of the Legendre's polynomial lies in the treatment of potential problems in physics. The potential at the point r, denoted by vector r, due to point charge q dash located at some other point r dash in the form of vector, is given by expression 1. Phi r is equal to 1 by 4 pi epsilon 0 q dash divided by mod of r minus r dash. We express the mod r in the form of square root of mod r square, and if you do that, please look into expression 2 in the denominator. This becomes a square minus a dot b plus b square in this form, that is here modulus r square minus 2 times r dot r dash, which is a dot product, plus mod r dash square under the square root sign. Assuming r is greater than r dash, we simplify expression 2 to get expression 3. Please note r dot r dash as a dot product is defined as mod r into mod r dash into cos theta, which is now seen in expression 3 in the denominator. And you take mod r dash square out of the radical sign, and what you get in expression 3 is 1 minus 2 cos theta mod r dash divided by mod r plus mod r dash divided by mod r whole square. You put r dash divided by r is equal to h and cos theta equal to x, and what we get is an expression 4 in the form q dash divided by 4 pi epsilon 0 mod r into 1 minus 2 x h plus h square to the power minus half. This expression, which is denoted by f x h in expression 5, is the generating function for the Legendre polynomial and is given by 1 minus 2 x h plus h square to the power minus half, which is equal to summation n equal to 0 to infinity h to the power n p n x. The expansion coefficient p n x are a set of polynomials of order n known as Legendre's polynomial, and the function f x h is known as the generating function for Legendre's polynomial. We next look into an alternative derivation of the generating function of the Legendre's polynomial. We look into expression number 6, which is a binomial expansion of 1 minus 2 x h plus h square to the power minus half. You can express this in the form 1 minus h into 2 x minus h whole to the power minus half. If we expand this in binomial, we will get 1 minus half h into 2 x minus h plus 1.3 divided by 2.4 h square into 2 x minus h whole square plus dot dot dot. The last two expressions are the n minus 1th and the nth term respectively. We now find the coefficient of h to the power n in the expansion of the nth term, which is 1.3 minus 1 divided by 2.4 into 2n into h to the power n into 2x minus h whole to the power n. Please note that if you expand 2x minus h whole to the power n, the first term will be 2x whole to the power n. All the other terms will contain h, and that is why the coefficient of h to the power n in the expansion of this is going to be 1 dot 3 dot dot 2 n minus 1 divided by 2 dot 4 dot dot 2 n into 2 x whole to the power n. What we do now in expression 7 is we take 2 common from each term in the denominator, and if you do that you get expression 8, which is 1 dot 3 dot 2 n minus 1 divided by 2 to the power n, because you have taken 2 common from each of the term in the denominator from expression 7, and divided by n factorial multiplied by 2 to the power n into x to the power n, which after simplification gives the expression 8. We next find the coefficient of h to the power n in the expansion of n minus 1th term, which if we simplify gives expression number 9. Now, please note, if we expand 2 x minus h whole to the power n minus 1, the first term is 2 x whole to the power n minus 1, and if you multiply it by h to the power n minus 1, it gives the coefficient of h to the power n minus 1, not h to the power n. Hence, we have to consider the next term, which is minus n minus 1 2 x whole to the power n minus 2, and hence if you multiply that by h to the power n minus 1, that term contains an h, and after simplification gives h to the power n. Hence, the coefficient of h to the power n in the expansion is given by expression or equation 9. If you simplify equation 9 on multiplying and dividing by 2 n divided by n, you arrive at equation number 11. Likewise, we can calculate more terms, and ultimately we will obtain after adding all the terms 1.3.5 dot 2 n minus 1 divided by n factorial multiplied by x to the power n minus n into n minus 1 divided by 2 into 2 n minus 1 x to the power n minus 2 plus n into n minus 1 n minus 2 n minus 3 divided by 2.4 2 n minus 1 2 n minus 3 x to the power n minus 4 minus dot dot dot, which is the expression for the Legendre's function of first kind or Legendre's polynomial of degree n. We have just derived the generating function for Legendre's polynomial. I hope it is clear. We now look into an alternate expression for Legendre's polynomial, which may be useful in many cases. We now look into an alternate form of Legendre's polynomial. As defined before, the Legendre's function of first kind is given by equation number 12. The general term is given by expression number 13. Now, please look into the third term of 12. The numerator is n into n minus 1 into n minus 2 into n minus 3. If we generalize that, we will be getting n into n minus 1 dot 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 n minus 2r minus 1, and if you open the minus sign, you will get n minus 2r plus 1. In the denominator term, you see 2.4 in the third term of expression number 12. If you generalize that to the rth term, since all are even numbers, it is 2.4 dot 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 2r. Similarly, if you see the next part, that is 2 n minus 1 into 2 n minus 3, if you generalize that, you will be getting 2 n minus 1 2 n minus 3 dot 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 2 n minus 2r plus 1. And the expression x to the power n minus 4 will give you x to the power n minus 2r. We now simplify the numerators and denominators of expression number 13. The numerator 1.3.5 dot dot 2 n minus 1, you multiply both numerator and denominator by 2.4.6 dot dot 2 n, which is given in equation number 14. If you do that, the first numerator is going to give you 2 n factorial, and the denominator is going to give you 2.1, 2.2, 2.3 dot dot 2 dot n after taking 2 common from each term, which is in equation 15. If you now take 2 common from all the n terms in the denominator, you will be getting 2 to the power n, and you will be left with 1.2.3 dot 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 n, which is n factorial. So, after simplification you will be getting 2n factorial divided by 2 to the power n into n factorial, which is given in equation number 16. Let us now take the numerator in equation number 13, which is n into n minus 1 dot dot 2n minus r plus 1. We multiply this expression by n minus 2r factorial, both numerator and denominator, as shown in equation 17. And if you do that, the numerator is going to give you n factorial and divided by n minus 2r factorial, which is given in equation number 18. We now take the denominator of 13, which is 2n minus 1, 2n minus 3, 2n minus 5 dot dot 2n minus r plus 1. You multiply this expression by 2n minus r factorial divided by 2n minus r factorial. If you do that, you get equation number 21, which is 2n factorial divided by 2 dot n, 2 into n minus 1, 2 into n minus 2 dot 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 2 into n minus r plus 1 into 2n minus r factorial. If we simplify this, we get expression number 23, which is 2n factorial divided by 2 to the power n into 2n minus 2r factorial multiplied by n minus r factorial into n minus r factorial. And after much simplification, we obtain expression number 24, which is 2n factorial divided by 2 to the power n into 2n minus r factorial into n minus r factorial by n factorial. If we now put all this simplified term, the general term 13 gives the expression given in equation number 25, which is minus 1 whole to the power r 2n minus 2r factorial divided by 2 to the power n into r factorial into n minus r factorial into n minus 2r factorial x to the power n minus 2r. Since p n x is a polynomial of degree n, we choose r in such a manner that n minus 2r is always greater or equal to 0, which implies r is less or equal to n by 2. Hence, the Legendre's function of first kind of Legendre's polynomial of degree n can be written in a more simplified form given in equation 26, which is p n x equal to summation r equal to 0 to n by 2 in a box into minus 1 whole to the power r 2n minus 2r factorial divided by 2 to the power n r factorial n minus r factorial n minus 2r factorial into x to the power n minus 2r, where n by 2 in the box means it will be taken as n by 2 if n is even and n minus 1 by 2 if n is odd. So, this is an alternative form of Legendre's function of first kind or Legendre's polynomial of degree n. We now determine few Legendre's polynomials, which we already have done before, but now with this new alternative form of Legendre's polynomial given in equation 27. Please note, if we put n equal to 0, then r equal to from 0 to n by 2, which actually becomes 0. So, the value of n and the value of r are both 0, which we put in the expression 27. And if you do that, you will be getting p 0 x equal to 1 by 0 factorial x to the power 0, which is 1. In the similar manner, if we put n equal to 0, n equal to 1 in equation 27, we will get p 1 x to the left hand side, and to the right hand side r is from 0 to half, which is again becoming 0, because you have to take n minus 1 by 2. And if you do that, you will be getting x to the power 1 divided by 1 factorial, which is x. In the similar manner, if you put the values of 1, 2, 3, 4, you will be getting the expressions 29, 30 and p 4 x and so on. We now look into few examples that will clarify the theory which we have learned in module 2. We now look into a few examples based on the generating function. The first example, we have to show that p n 1 is equal to 1. The generating function for Legendre's polynomial is given by equation number 31. Now, you put x equal to 1 in the expression of 31, and if you do that, we will be getting 1 minus 2z plus z square to the power minus half in the left hand side of 31, and to the right hand side you will be getting summation n equal to 0 to infinity z to the power n p n 1, which is given in equation number 32. Now, the left hand side of 32 can be put in the form 1 minus z to the power minus 1. If you do that, you expand it, you will be getting equation number 34, which is 1 plus z square plus dot dot z to the power n plus dot dot dot, and the right hand side is summation n equal to 0 to infinity z to the power n p n 1. If you equate the coefficient of z to the power n from both sides, we get p n 1 to the right hand side, and to the left hand side it is 1, and hence we prove that p n 1 is equal to 1. Our second example, we have to show that p n minus x is equal to minus 1 whole to the power n p n x. Again, we start with the generating function for the Legendre's polynomial, which is given by equation number 35. What you do here is, first you replace x by minus x in 35, and if you do that, you will be getting 1 plus 2x z plus z square to the power minus half equal to summation n equal to 0 to infinity z to the power n p n minus x, given by equation number 36. Again, you replace z by minus z in 35, and we get 1 plus 2x z plus z square to the power minus half, which is equal to summation n equal to 0 to infinity minus z whole to the power n p n x, which is equation number 37. What you do now is, in equation 36 and equation 37, the left hand side have the same expression. So, we equate the right hand side in from equation 36 and equation 37, and if you do that, you will be getting equation number 38. The left hand side is summation z to the power n p n minus x, and the right hand side is summation n equal to 0 to infinity minus 1 whole to the power n z to the power n p n x. And if you equate the coefficient of z to the power n from both sides, we will be getting p n minus x equal to minus 1 whole to the power n p n x. If you put p n 1 equal to 1 and putting x equal to 1 in the above equation, which is 39, we will be getting p n minus 1 equal to minus 1 whole to the power n, which has been asked to derive in the second part of the problem. Our next example, we have to show that p 2m plus 1 equal to 0 and p 2m 0 is equal to minus 1 whole to the power m 2m factorial divided by 2 to the power m m factorial square. We again start with generating function for Legendre's polynomial given by equation number 41. We replace z by minus z in equation 41, and we get 1 plus 2x z plus z square to the power minus half, which is equal to summation n equal to 0 to infinity minus z whole to the power n p n x. Putting x equal to 0 in equation 42, we get summation z to the power n p n 0 equal to 1 plus z square to the power minus half. This we expand by binomial to get minus half into minus half minus 1 dot 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 minus half minus n minus 1 divided by n factorial z square whole to the power n, which is given in equation number 44. If we simplify the expression, we will be getting equation number 45, which is summation z to the power n p n 0 equal to summation n equal to 0 to infinity minus 1 whole to the power n 1.3.5.2n minus 1 divided by 2 to the power n into n factorial into z to the power 2n. Now, to get the first expression, we equate the coefficient of z to the power 2m plus 1, which is an odd number, from both sides of 45. And if you do that, to the left hand side you will be getting p 2m plus 1 0, because n is replaced by an odd number 2m plus 1, whereas to the right hand side z to the power 2n, that is all the powers are even. Hence, we do not get any coefficient of z to the power 2m plus 1 from the right hand side of 45, and hence the right hand side is 0. Therefore, we just show that p 2m plus 1 0 is equal to 0. To prove the second part of the problem, we equate the coefficient of z to the power 2m from both sides of 45. The left hand side is p 2m 0, and the right hand side is minus 1 whole to the power m 1.3.5.2m minus 1 divided by 2 to the power m into m factorial. What we do is we multiply this expression in 46 by 2.4.6.2m, both numerator and denominator, and if you do that, the numerator becomes 2m factorial, the denominator becomes 2 to the power m into m factorial multiplied by 2.1, 2.2, 2.3.2.m, which is obtained if you take 2 common from all the m terms in the denominator given in 48. And if you simplify this, you will be getting minus 1 whole to the power m 2m factorial divided by 2 to the power m into m factorial into 2 to the power m into m factorial, which is given in equation number 49. And after simple process simplification, we get minus 1 whole to the power m 2m factorial divided by 2 to the power m into m factorial square, which is needed and the proof of part 2. Our next example, we have to show 1 minus z square divided by 1 minus 2xz plus z square whole to the power 3 by 2 is equal to summation n equal to 0 to infinity 2n plus 1 z to the power n p n x. As before, the generating function for Legendre's polynomial is given by equation 50. We now differentiate this expression with respect to z both sides, and we obtain z minus x into 1 minus 2xz plus z square whole to the power minus 3 by 2 equal to summation n equal to 0 to infinity n z to the power n minus 1 p n x. We now multiply both sides by 2z and we get expression 51. We now add 50 and 51 to obtain 1 by 1 minus 2xz plus z square to the power half plus 2z into x minus z divided by 1 minus 2xz plus z square whole to the power 3 by 2. If you simplify this, what you will be arriving at expression number 52, and further simplification will give you equation 53, which is the desired result. Example 5 is a bit different from which we have done in the previous examples. Here we have to show p n minus half is equal to p 0 minus half into p 2 n half plus p 1 minus half into p 2 n minus 1 half plus dot 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 p 2 n minus half into p 0 half. We start with the generating function for Legendre's polynomial given in equation 54. Next, you put x equal to half and x equal to minus half respectively in expression 54, and if you do that, you will be getting equation number 55 and equation number 56. Next, you replace z by z square in expression number 56, and if you do that, you will be getting 1 plus z square plus z to the power 4 to the power minus half equal to summation n equal to 0 to infinity z to the power 2n p p n minus half, given by equation 57. Now, we can simplify this 1 plus z square, which can be written as 1 plus z square whole square minus z square, which is equal to, use the formula a square minus b square equal to a plus b into a minus b, and you will be getting 1 plus z square plus z into 1 plus z square minus z, and we get equation number 58, which implies that summation n equal to 0 to infinity z to the power 2n p n minus half, which is obtained for expression 57, is equal to summation z to the power n p n minus half into summation z to the power n p n half, which we get from equation 55 and equation 56. What we do now is we substitute the values, we expand the summation n equal to 0 to infinity z to the power n p n minus half multiplied by summation n equal to 0 to infinity z to the power n p n half in equation 60, and if you do that, you will be getting equation 61. Next, we equate coefficient of z to the power n from both sides. From the left hand side of expression 60, it is clear that the coefficient is z to the p n minus half, whereas to the right hand side, if you multiply the two expression, please note that the first expression p 0 minus half, if it is multiplied by z to the power 2n p 2n half, only then you will be getting a coefficient of z to the power 2n, and hence the right hand side becomes p 0 minus half into p 2n half plus p 1 minus half into p 2n minus 1 half plus dot 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 p 2n minus half into p 0 half. And this concludes the proof of our example 5. The final example, we have to show that 1 plus z divided by z into 1 minus 2 x z plus z squared to the power half minus 1 by z is equal to summation n equal to 0 to infinity p n plus 1 x plus p n x whole multiplied by z to the power n. As usual, we take the generating function given by equation 62. Next, we take the left hand side, which is 1 plus z divided by z into 1 minus 2 x z plus z squared to the power half minus 1 by z. What we do now is we divide 1 plus z divided by z, and you will be getting 1 by z plus 1 multiplied by 1 minus 2 x z plus z squared to the power minus half minus 1 by z. Next, you express 1 minus 2 x z plus x square plus z squared to the power minus half by 62, and you will be getting an expression as shown in equation 64, which is 1 by z summation n equal to 0 to infinity z to the power n p n x plus summation n equal to 0 to infinity z to the power n p n x minus 1 by z. What you do now is you expand the summation, the first summation of equation 64, and if you do that, you will be getting equation number 65. We now put p 0 equal to 1 in equation 65, and what we get is equation number 67 as 1 by z into 1 plus summation z to the power n plus 1 p n plus 1 x plus summation n equal to 0 to infinity z to the power n p n x minus 1 by z. If you open the bracket, you will be seeing that you get an expression 69 with 1 by z and minus 1 by z, which cancels out and gives you equation number 70, which is our desired result. Summing up, in module 2, we learned about the generating function of the Legendre's polynomial. We have also seen an alternate expression for Legendre's polynomial, followed by some examples. In module 3, we will take up the recurrence relation, which is also another important aspect of Legendre's polynomial. Thank you.